What if the universe could exhale, and we felt the hush of that breath on our cheek? Tonight we drift toward a lullaby called "This is the biggest ever eruption in space," where dust gleams like frost and pale veils hang in gentle pillars of light. I'll take your hand past Jupiter's pull to Io, kneaded by tides until sulfur fires bead and bloom. Then to Enceladus, an ice pearl whose skin cracks and feathers plumes, a hidden ocean tapping the rim of Saturn's song. And farther, to Triton, Neptune's backward traveler, where dusky plains whisper and cold geysers write faint cursive on the dark. We'll hold these breaths of worlds beside our own Hunga Tonga rising out of blue water, so the meaning of eruption feels close, kindly, and alive. Voyager, Galileo, Cassini, new horizons will guide our steps. If your heart says yes, a quiet like and a soft subscribe would be lovely. Now let your eyes fall heavy. We'll begin together, unhurried and warm. Imagine you're standing at a quiet window, the room dim and kind, your breath slow and steady, and the sky is taken by a giant no, not our moon, but Jupiter itself, hanging like a pale golden cloud that fills almost the whole view. From Earth, that sight can't happen. From the surface of Io, Jupiter would loom 39 times wider than our familiar circle of light. Io lives close to the planet's cloud tops, about 350,000 kilometers away. So close that the heavens feel tilted toward it. So close that even the ground seems to listen. In that hush, you can almost hear a soft pull and release, like a blanket being smoothed by careful hands. Jupiter's gravity, joined by Europa and Ganymede, kneading Io in an ancient rhythm. Time moves differently here. Io completes a lap around Jupiter in about 42.5 hours, 2 Earth nights, and a whisper more. And, like our moon, it keeps one face always turned toward its parent. That steady gaze doesn't bring peace. Beneath the appearance of stillness is a restless body. Io's path is slightly oval, and that small imperfection is no accident. It keeps time with its siblings. Io circles twice for every Europa orbit, and 4 times for every Ganymede orbit. A 1, 2, 4 resonance that sounds like stringed notes held in tune. That resonance tugs the orbit imperfect, never quite letting it relax. Each close approach stretches the moon. Each farther reach lets it slacken. Shape changes become heat. Rock becomes a slow bellows. And warmth gathers where the shell is thin, where seams are weak, until the ground gives it back as fire. If you could place your palm against Io's crust gently, the way we place a hand on a sleeping shoulder, you'd feel a world that does not truly sleep. At certain moments in the orbit, the solid tide, the literal bulge of Io's body, can rise on the order of 100 meters. On Earth, the moon lifts and lowers our seas by a few meters. The sea flexes and returns. On Io, the tide is rock itself, worked and reworked by Jupiter's pull and the timing imposed by the other big moons. The effort of that flexing turns into heat within the mantle, a steady stoking that feeds hundreds of volcanic vents. Plumes of sulfur and sulfur dioxide burst upward, flowers of smoke unfolding against black space, then drift and settle as faint yellow frosts. Io is not a quiet desert. It is a page being rewritten, again and again, in the handwriting of lava. People often begin Io's story with the crowd and then walk inward to a single name. Around Jupiter, moons gather in profusion, scores of them. tucked among rings and drifting farther out in irregular paths. 4 are grand and old to our eyes. The Galilean moons first marked in a telescope in 1610, Io, Europa, Ganymede, and Callisto. Set them in a line beside their planet, and each sings a different line of the same song. Gravity, time, light. Io, closest in, sings the fastest line, the one that needs breath and keeps taking it. Under certain lights, the sky above Io glows. Not the sapphire and violet curtains we call aurora on Earth, but a thin, tarnished halo, where energetic particles thread Jupiter's magnetic field and brush Io's escaping gases. The atmosphere is fragile, sulfur-rich, constantly replenished by eruptions. Sulfur dioxide rises and freezes. Flakes fall out of the air and dust the plains like pale ash. Lava darkens and then lightens under each new snow of sulfur. When plumes soar hundreds of kilometers into space, they sketch faint parasols that collapse and rain back down. The canvas never stays still. A dark fan of cooled basalt spreads here. A bright halo of frost blooms there. And between them soot-brown and saffron patches tell of chemistry that happens when heat meets air starved of water. Io's size invites a moment of misreading. It is comparable to our moon, and that familiar scale tempts us to imagine a similar calm. But Io is denser than any other moon we know. Density is a quiet kind of truth. It says, rock and metal live here, in greater measure. No deep reservoirs of water ice soften its bones. Where other large moons are mixtures of ice and silicate cold, yielding a little under tidal kneading, Io is dry to the point of austerity. Its very air is built from sulfur. Its colors, mustard, rust, obsidian, are the palette of heat that met a barren shelf. The lack of water makes the crust take stress like pottery. It cracks and groans and vents without cushion. What would be a slow creep in an icy world becomes a fracture here, and from the fracture, a fountain. Inside, picture a metal heart, iron, perhaps iron with sulfur wrapped in a silicate mantle, capped by a rocky crust. That core is likely quiet in magnetic terms. If it were convecting strongly, it might generate a magnetic field of its own. But Io shows no such self-made shield. It moves instead through Jupiter's immense magnetosphere like a leaf in a steady wind, not generating the wind, yet trailing a faint, conductive wake. Near the top of the mantle, rock softens with heat. Somewhere above, at least tens of kilometers below the surface, a partially molten layer may spread, a warm reservoir where magma gathers and waits. Tides pump, fractures open, and the waiting ends in a plume. Look closely. Names flicker on the map like embers. Pele, Loki, Prometheus. Not myths here so much as living engines. Their behavior changes with the rhythm of the orbits. When Io's eccentric path brings stronger stretching, pressure rises in magma chambers. Cracks ease open. Sulfur dioxide gas drag lifts dust and droplets into towering fountains. The sprays carve out gray arcs that thin with distance, sometimes reaching heights that dwarf earthly thunderheads. The ground nearby reddens with fresh deposits, then darkens as the hot skin cools, then fades back under the next fall of pale sulfur snow. You could sit and watch for a while, an hour, a day, a week, and still the face would alter under your gaze. Why is Io so feverishly alive while its siblings are gentler? The answer rests like a pulse beneath your fingertips. Distance, resonance, unending stress. If Io's orbit were perfectly circular, the squeezing and relaxing would quiet, heat would seep away, and the fire would dim. But Europa and Ganymede hold Io's path just off-round, like friends keeping time in a clapping game that never stops. Jupiter's vast mass conducts the whole ensemble. The result is a world that cannot shrug off its warmth. The bellow keeps moving. The furnace never truly idles. Auroral edges speak softly of another bond. As gases stream from Io, some are stripped, some are excited into glow, and some are swept into a plasma torus that girdles Jupiter. At times, electric currents trace field lines between planet and moon, invisible ropes that only sensitive instruments can feel. Imagine a near-silent harp strung across space, where charged particles are plucked by motion. Io is both player and string. It feeds the instrument and it vibrates upon it. When eruptions multiply, the halo brightens, a thin crown shifting color. When Io passes through denser parts of the magnetosphere, the crown stirs again. Even in the dark, the connection hums. Dryness is not just a fact about chemistry here, it is character. Where water is absent, heat finds fewer graceful exits. The crust accepts strain more directly. The air forms from gases divorced from oceans. The surface paints itself with compounds that speak of fire and mineral, not of frost. Turquoise seas and gentle glaciers belong to other moons. Europa, Enceladus, Triton carry their hidden waters. Io's stories are written in scoria and frost of sulfur, in glassy lavas and paper-thin snows. Some plains look like chalk dusted over slate. Elsewhere the land is lacquered black, a sheen where liquid rock once ran, now stilled and brittle. Daylight warms the surface thinly, thickening the atmosphere as sulfur dioxide sublimates. Night cools and the breath condenses. A new eruption puffs it back again. The whole envelope is a veil that changes with the hour. Close your eyes and listen inward, guided by what our brief visits have taught. A plume once caught in silhouette, an umbrella lifting over the limb. A hush in the charged particles. A small give in the field where a conducting body must be. Heat mapped as patches and ribbons, bright enough to name fresh lava at midnight. From those clues, an inner sketch stays steady. A largely non-convecting core, a mantle threaded with warmth, and near the surface, a zone of partial melt, tens of kilometers deep, where magma gathers and seeks faults that tides have already loosened. Keep a few anchors in your palm. Io is close to our moon in size, the densest moon we know, circling Jupiter in about 42.5 hours. From Io, Jupiter swells 39 moons wide. The solid body itself rises and falls by roughly 100 meters under stress. A 1, 2, 4 rhythm with Europa and Ganymede keeps the orbit a little off-round, and that small imperfection keeps the heat. With that in mind, Io stops being a hellscape and reads like a living body coached by gravity's firm hands. Stretch into warmth, warmth into eruption, eruption into lines of fresh ash and glass. Jupiter stands close and enormous, silent, sufficient, turning small deviations into rock tides, auroral crowns, and a surface that rewrites itself in sulfur light and lava script, which is why the part that steals the breath is the part that never sleeps. Hundreds of volcanoes, embered wells, scattered across the skin, each a door where heat speaks. Long before we watched them flare, we had only hints, telescopes sketching a dry world without a soft shoal of ice. a face stained yellow and rust by sulfur. The rest was night and guesswork, until a small craft drifted close enough to thin the night and let the first true images arrive. One traveler felt the place first in a rough way. Pioneer 11 slid through Jupiter's domain and glimpsed Io with eyes that were far from perfect, yet sure enough to whisper two truths. The moon was made of rock, not ice. The air was a veil, not a blanket. Its sibling, Pioneer 10, meant to take close portraits, crossed a river of radiation that drowned the commands mid-journey. The electronics faltered in a storm that was 10,000 times stronger than the worst the space around Earth can offer. Imagine being a moth skimming the rim of a furnace. The light is knowledge, the heat is peril. Those early steps were clumsy, brave, and they charted the edges of a world that was about to show its heart. When Voyager 1 arrived in 1979, it passed not much farther than the breadth of a continent. From Io around 20,000 kilometers, and the cameras woke like eyes in the dark. The images came back wild with color, like a painter's drop cloth after a long day. Saffron plains, rusty fans, black glassy flows, white patches like frost. What wasn't there mattered. Two almost no impact craters at all. The usual pockmarks of old surfaces scraped away by something busier than time. Mountains rose higher than Everest. Pits broad, dark-walled depressions spread for hundreds of kilometers, as if someone had pressed a slow thumb into warm clay. And there, reaching beyond the curve of the limb, were feathered umbrellas of material lifting into space. Plumes, not relics, but acts. For the first time beyond Earth, leaving aside the code language of cryovolcanoes, a world was caught in the middle of eruption. In those frames, the story turned from rumor to voice. The absence of craters became a sentence. This ground is young. The flowing shadows became another. Lava has moved here, recently enough that it still holds the night's heat. The high mountains, blocky, step-sided, suggested a crust that breaks and heaves. Not a calm sheet of ice, but it was the plumes that changed how we breathed. They rose hundreds of kilometers and spread in pale parasols, faint at the edges, graceful in their reach, too large to ignore and too delicate to forget. Space is quiet, but these were movements you could almost hear. A few months later, in July of the same year, Voyager 2 drifted past at a greater distance, about 1 million kilometers, and still found 7 of the 9 fountains that Voyager 1 had seen in March. Think of it. 4 months, and they were still there, still breathing. Activity wasn't a spark. It was a season, perhaps a system, with its own timing and its own patience. The moons farther out took their places as listeners. Jupiter watched like a massive lamp. Io kept rewriting its face between 2 passings. The colors that startle the eye have tender causes. Sulfur compounds salt the surface. They lay down yellows and oranges, rusty reds where they've been cooked or irradiated, whites where fresh sulfur dioxide frost has settled. Voyager painted Io in that palette and confirmed that the thin, shifting atmosphere is dominated by those same sulfur species. Closer to the poles, harsh radiation bites at the frost and breaks it down. The reds deepen, the whites thin. The skin shows the work it has endured. Elsewhere, the world wears the souvenirs of its own fireworks. Rings and blotches where plumes fell back as powder, stains in 100 shades of ochre. This is not the blue-white purity of an icy moon. This is the mineral warmth of a kiln's interior. Years passed, and another visitor came to stay. In 1995, A craft slid into Jupiter's gravity well and called the whole system home, Galileo. It wasn't built as a lover of Io alone, yet it turned its lenses often toward that restless ground. Its high-gain antenna failed to open properly. Its voice back to Earth was quieter and slower than planned. Yet, over time, it gathered some of the sharpest views we possess. There are blessings even in limitation. When a machine must whisper, it learns to choose its words. Galileo saw plumes, many of them. It watched patches brighten and dim. Hot spots breathe in the infrared. Edges change between one pass and the next. It confirmed what the colors had promised. Eruptions on Io throw both sulfur and silicate magmas, cousins to earthly lavas, but seasoned with richer magnesium and set in a world where the air itself is a sulfurous sigh. Under Galileo's gaze, the surface became a book of textures. Yellow plains, sulfur laid down like pollen spread wide. White pools, fresh sulfur dioxide frost gathered in patches and along slopes kept cool. Near the poles, the colors skewed red, not for romance, but for radiation damage, chemistry broken and remade under the rain of energetic particles. Elsewhere, you could trace the arc of a plume in its aftermath, a ring of deeper red, where the fallout was thickest, fading to peach, then straw, then the ordinary yellow of quiet days. It felt as though each eruption wrote a circle poem, a set of widening lines around a single breath of heat. One of the boldest poems has a name we borrowed from old fire, Pele. The deposit around it is unmistakable, a broad red crown laid over the land. When Voyager 1 looked, a plume surged there, a column that climbed roughly 300 kilometers high and spread to about 1,200 kilometers across, an umbrella the size of Alaska drifting just above the limb. By the time Galileo kept its long watch, Pele slept. The crown remained, a lacquered memory. You don't miss the fire entirely. You read the ash, you read the stain, you read the way light lies on the field that was once a fountain. Other names flicker like campfire sparks. Prometheus, with its persistent lava flows meeting frost and making steam-sown streaks. Loki, Patera, a dark lake whose brightness rises and falls as a vast crust overturns in slow, luminous waves. Unnamed calderas that open like windows across the plain. Notice something odd if you're used to Earth. On Io, the sources of flow so often sit low, within broad depressions called paterae, not perched on tidy cones. The tallest peaks here often lack summit craters altogether. They are tilted blocks and stacked slabs raised by deep stresses, while eruption favors the edges, the faults, the places where tides pry. It's as if the mountain carries a long history of force, but the fire prefers to whisper through the floor. Even the quiet parts of the story are full of motion. The thin air thickens in sunlight as sulfur dioxide sublimates, then thins again in night as it condenses to frost. Eruptions puff more gas into the mix, and the balance sways. Charged particles from Jupiter's magnetosphere thread through and around this veil, tangle with it, excite it, and the edges glow. Aurora not in curtains, but in halos. The plumes themselves rise ballistically grains, and molecules tossed by heat, then traced by gravity and land downwind as gentle snow. The whole cycle is a breathing. Lift, spread, fall, rest. Then again, driven by the drumbeat of resonance that never lets the interior entirely cool. Think of the engineers who sent the cameras. Pioneer's near failure was a lesson in how fierce Jupiter's neighborhood can be. 10,000 times Earth's worst radiation is not an exaggeration. It's a lived environment where bits flip and sensors stumble. Still, The next pair, Voyager 1 and 2, threaded the gauntlet and carried back portraits so close you could see the land bruise under a fresh fall of material. And Galileo, patient through its mechanical misfortunes, watched long enough to catch the rhythm rather than a single note. From these glances, a personality emerges that no telescope alone could grant. Io the restive, Io the painted, Io the maker of its own weather in a vacuum. When you look at the pictures with soft eyes, details come forward the way embers brighten when you lean. A flow field snakes outward, dark as cooled coffee, with brighter margins where it met frost and glazed it. A red ring thins toward one side, telling of wind or the steering of trajectories by rotation. A mountain casts a shadow twice the length of anything nearby, hinting at a height that would challenge even human air. Pits with sharp rims and terraced walls suggest collapse over emptied pockets, reservoirs that fed the last outpouring and then withdrew. None of this is noisy. It is page-turning without a hand, the text rewriting as you read. What began as guesses from earth dryness, sulfur now stands as a felt world. Dryness is the stage where heat acts without cushion. With no deep water to lubricate or cool, the crust takes strain directly, fractures cleanly, and lava chooses open gashes in rock rather than tunnels in ice. Sulfur is both paint and breath-coloring ground, thickening daylight air, etching rings as plumes fall. Keep the anchors light in your hand. Voyager 1 sweeping within 20,000 kilometers. Voyager 2 keeping a 1,000,000-kilometer watch. Pele's plume, 300 kilometers high and 1,200 wide. Mountains overtopping Everest. Pits the size of small countries. They're not there to crowd you, only to steady the picture. All of it returns to a body that cannot be still. Resonance keeps Io's path just off-round twice for Europa, 4 times for Ganymede, turning shape change into warmth. Warmth softens stone, softness seeks seams, seams become vents, and vents draw patterns on land, while momentary crowns lift into sky. The crowns fade, the patterns brighten, and Jupiter turns immense, silent, a nearby star that isn't its magnetosphere humming like wires in wind. In that hum, instruments hear plume signatures. In heat maps, fresh black glass appears. Invisible light, new stains quietly overwrite the old. Sit with that, and the scale settles. A moon our moon size, dense and quick. Mountains and pits rising and falling like breath. The volcanoes are not shy. They punctuate every paragraph rings, fans, lakes, polar tints, equatorial girdles, crowns the size of states, umbrellas wide as countries. Early craft was singed, later ones learned to listen. Together they taught us to read a surface always mid-becoming. And just beneath a field of pale frost, you can almost feel the next plume gathering, waiting for gravity's steady hand to squeeze and let the breath show again. Which is why, up close, the heat's handwriting is not cones but basins, lava that lies wide and low, pooling into dark inland seas with high rims, like calm water in a black bowl. Loki is the grandest, a roughly 200-kilometer depression, a city-to-city span, beating like a readable heart. It isn't a lake in the earthly sense, but the open roof of a magma reservoir, usually skinned by a thin, fragile crust that floats. Most nights the lid holds cracking, sealing, leaking heat in a steady hush so that Loki alone carries roughly a quarter of Io's average heat to space. Then the quiet fails. The cooling plate grows heavy, a line weakens, and the raft founders tilts, breaks, and sinks back into the molten dark. For a while, the basin becomes a lantern without a shade, and Loki's glow leaps to tenfold, a flare so sudden, distant instruments record it as if a giant hand had turned the universe's dimmer up in a single smooth twist. This overturning, the sudden surrender of crust back into fire, doesn't belong to Loki alone. At Tvashtar, one of Eo's other wide, dark cradles, the same story plays out with more drama, as if the stage wanted an audience. On quiet days, Tvashtar looks like a dusky oval with textured edges, a calm eye in a saffron face. But there are moments when the skin caves in and the magma below shows itself in a sheet. In such moments, even a camera designed for cold stars can't keep its composure. The radiant curtain is so intense that pixels go to pure white, detail burned away by brightness. What remains is the outline of a phenomenon, a seam where the crust fell, a glare where the lake breathed flame, and a feeling that on this world, lids are only pauses, never stops. Sometimes the universe offers us a front row seat without warning. In 2007, a small craft on its way to another story paused beside Jupiter to borrow speed. New Horizons, bound for Pluto, slipped through the neighborhood like a courteous guest, testing the doorbell and cameras before heading on. It glanced at Io and caught Tvashtar in full voice. The plume lifted broad, wild, splendid hundreds of kilometers above the surface, an umbrella of ash and gas unfolding into the darkness. You could see smaller flares elsewhere, freckles of eruption that reminded you the moon is not a single blaze but a choir. For many of us, that sequence of frames became one of those rare things in space that feel both impossible and undeniably real. A fire fountain in a vacuum, frozen by distance, yet visibly alive. For all that the volcanoes sprawl and the lakes sit low, Io also carries mountains with a stark, improbable posture. The tallest reaches about 18 kilometers into the thin air twice, and more the height of Everest, above sea level, and many stand by themselves. Isolated blocks shouldering upward without the comfort of a range. They don't tend to be volcanoes. Their shapes are blunt, their faces fractured, as if titanic slabs of crust were wedged up by forces below and left to stand. And yet around their feet, you often find lava lakes, calderas, and flow fields, as if the same faults that hoisted the peaks also open doors for magma. The mountains are history written in tilt and pressure. The lakes are the present tense, sentences that keep adding clauses. All of this heat and motion takes place not in emptiness, but within an invisible weather, a magnetic sea, so large and strong that most of us meet it first through metaphors. Jupiter's magnetosphere is vast. Io orbits within some of its densest, most forceful regions. The moon's thin atmosphere and its eruptions shed particles, sodium, oxygen, sulfur compounds that drift off into space. Many remain electrically neutral at first, and together they form a tenuous cloud that trails and precedes Io along its path. A breath that doesn't disperse quickly because it's moving with the world that exhaled it. Farther out, and all around, is a different kind of ocean. A plasma torus, a donut-shaped ring of charged particles that ride the rotation of Jupiter's magnetic field. That ring spins much faster than Io orbits, on the order of 70 kilometers per second against Io's 17. So the torus effectively sweeps past the moon like a river current passing a swimmer. Where the fast, charged flow meets the neutral cloud, sparks of a sort are made. Collisions and encounters strip electrons, flip states, and wake atoms into ions. Those new ions don't remain aimless. Magnetic field lines gather them, and they join the torus, thickening it with fresh material drawn from the moon's own exhalations. The exchange is steady enough to count in familiar terms. Roughly a ton of matter each second leaves the neutral cloud to become part of the plasma torus, a soft rain of atoms turning into a current-carrying sea. Enriched like this, Jupiter's magnetic influence swells and stiffens. If such a thing were visible to our eyes from Earth, if the magnetosphere were painted like a ghostly lantern in the sky, it would span a size not unlike the moon's disk. We seldom get to see it directly. We live in its effects instead. The coupling between moon and planet goes deeper than a shared sea. Magnetic field lines thread space like taut strings, and as Io crosses them, a path of electrical connection is traced, what physicists call a flux tube, a bundle of lines where current prefers to flow. You can imagine it as a luminous braid if you like, not because it shines in the way a lamp shines, but because charged particles race along it as if a channel had been cut just for them. On the sun, flux tubes loop between sunspots. You see the arcs in extreme ultraviolet, hot plasma outlining the invisible bones of magnetism. Between Jupiter and Io, the effect is gentler to the eye, but no less real. Current runs. Energy is deposited. In Jupiter's polar upper atmosphere, where the tube's footfalls land, auroral spots bloom bright footprints that mark where the connection meets air. Watch those polar regions and you see more than a single dot. An auroral tail arcs around, a trail that tells of motion and timing, an elegant record of the moon's path written on the planet's poles. The footprint brightens when Io's activity is high, dims when it quiets, shifts with the magnetospheric weather like a candle flame in a draft. Color, too, becomes a language. On Io itself, aurora shimmer not only at the poles, because the atmosphere is so thin and the sources of energy so intimate that excitation can happen in many places. The hues tell you which atoms are being nudged into glow: greens from sodium, reds from oxygen, blues whispered from sulfur, each line a different voice in the same choir. Space is not silent. It sings in wavelengths your eyes can learn to imagine. Return, for a moment, to the lakes and their lids. The thin crust that forms atop a lava sea is a compromise between heat rising and space cooling. It thickens as long as the heat is steady and the surface can radiate. But the lake is fed from below by tides made into warmth. New magma wells up, changes the buoyancy, and undermines the raft. When a crack runs and the balance fails, plates tilt and sink in a procession, like dark ice flows slipping underwater. The line of foundering travels across the lake over days or weeks, a moving edge where incandescent rock is briefly naked to space. In the infrared, the brightness surges. In visible light, the scene can white out because the sensor's well is shallow compared to the furnace it's asked to measure. On Io, overexposed is not a mistake, it's a signature. Even the flatness of many eruption centers has its own grace. Basins tend to collect flows, faults prefer to open at low places where tension focuses, and the lack of tall cones tells you the eruption style is often effusive, sheets and lakes rather than columns of piled ash. The high peaks, raised by blocks splitting and tilting, speak of tectonics driven by compressions and shears induced by tides. It's a different baking than on Earth, where plates ride convection and water oils the hinges. Here the oven is gravity's hand. Here the hinges are dry and stiff. Here the relief can be sudden, a mesa heaved up, a wall thrown askew. Those who flew by brought back more than numbers. They brought small, perfect moments that sit beside your pillow years later. The new horizons, plume lifting into the dark like a silvered fountain, grains arcing in ballistic, tender paths. The bleach-white frame where Tvashtar's curtain overwhelmed a censer. Loki's long, patient, brightening. Then a sudden sweeping dim as the overturned front completed its trip and a new crust once again sealed the lake. These are not just data, they're breath and exhale, proof that a world with no seas can still have tides. That rock can remember a rhythm and return it to the night in heat. Out in the Taurus, ions born from Io ride the magnetic rotation like leaves in a gyre. Their circulation feeds back into the larger weather. Radio emissions from Jupiter wax and wane. The auroral ovals pulse with slight changes, the way your pulse quickens when you climb stairs. Instruments count rates and energies. Your mind hears the music instead. A ton per second sounds like a quarry's worth of stone. But here, it's a mist, a steady sip from a moon that makes more from tides than it loses to space. The loss is part of the connection. The connection is part of the life. Without it, auroras dim and tubes fall quiet. With it, the system becomes one body, planet, field, moon, and flame, tied by cords you cannot see but can learn to feel. Keep 3 images of Io within reach. A black lake with a fragile lid, high-rimmed and bright-hearted, where crust remembers it's only visiting and slips away. A lone mountain, shouldering 18 kilometers into thin light, ink-dark flow fields pooling at its feet, and a shadow bridge, Io's flux tube carrying current to Jupiter's polar air, where a footprint blooms and fades like a heartbeat seen through snow. Between them runs a river of particles, neutral becoming charged, charged becoming current, looping the giant world. Some nights, the science folds into one quiet sentence. Lids sink, light rises, and a circuit closes between a fiery moon and a magnetized giant. The honest weights stay small and steady, 200 kilometers across, a quarter of a world's heat, 10-fold surges, plumes reaching hundreds of kilometers, peaks near 18. A plasma stream around 70 kilometers a second, sliding past a moon at 17. About a ton a second feeding the ring. Hold them like smooth stones. Let the story settle around them. What remains is a warm understanding. Io is not just eruptions, it's connections. Crust to reservoir, lake to lid, atom to field. A moon's breath to a planet's aurora. And in the hush, with Jupiter's unseen harp humming, that web feels as certain as your own breathing, reminding us that eruptions, whether in vacuum or air, are ways worlds speak. So when the map turns from space to sea, the ear is already trained for the next voice. By late December, the water-dark crescent of Hunga Tonga Hunga Harpi began to stir a tremor under the Pacific's breath that islanders felt in their bones. Evening waters looked calm. The volcano below did not. Pulses rose like a slow throb you notice only when the room is quiet. Local scientists watched the small surges and dusky plumes, and the calendar slid toward the new year with a hush that felt expectant rather than still. On January 14, the mountains spoke out, where ocean and sky touch. From nearby boats and coasts, the sight felt immense. Ash driven 20 kilometers up, a straight gray pillar launched into the lower sky, widening at the crown, casting a soft dusk over the blue. Up close, the column seemed to own the horizon, but from above, from satellites keeping their patient vigil, it looked like a thin pinprick, a hairline scratch on the planet's skin. Perspective is a teacher with gentle hands. What overwhelms us at the shoreline can look like a breath from orbit, and what seems small from far away can change the day of every household beneath it. The next day, the quiet ended with a wordless shout. 2 geostationary sentinels goes west over the Americas and Himawari 8 over the Pacific, caught the moment in synchronized vision. A brilliant, circular bloom flowering from the sea, shock fronts rippling outward like stones cast into a cosmic pond. In a few frames, the ash canopy expanded so fast, it felt unreal, a gray-white anvil racing beyond the island ring. Early estimates spoke in superlatives. It might rival, perhaps even dwarf, the largest human-made blasts we've measured. It isn't hard to see why. Lay the cloud across a map of Europe, and it would blanket a subcontinent. Small countries vanish beneath a single breath of stone turned to sky. Lightning found the plume the way swallows find warm air. Radio sensors counted more than 200,000 flashes in that ash-burdened sky. Staccato light stitching through smoke, discharges hidden beneath the canopy, while satellites trace their signatures like a cardiogram. Volcanic lightning is a topic still learning its own language. The stage is a violent mixing of ash, steam, and fractured droplets. Particles collide and separate charges. Ice forms and shatters. The plume rubs itself into a storm. Scientists suspect that both the eruption itself and the plume's inner weather feed the charge, a double engine of sparks working above a boiling sea. The island that did the shouting was uninhabited, a rim of new land lifted by earlier eruptions. But no eruption is alone. It writes on neighbors. Ash is the first handwriting, and it carries a museum of hazards. On Tonga Tapu, Ewa, and islands across the kingdom, a fine gray snow fell and kept falling, turning gardens and roofs the color of a lunar plain. Photographs taken before and after are cruel in their honesty. Greens gone to grays, turquoise lagoons dulled to pewter, palm fronds bowed under weight they were not bred to bear. Residents were told to stay indoors while the ash fell. A mouth and a lung deserve gentleness, and ash is a dusty knife when it is breathed. Catchments and open tanks took the first wounds, thin films on water, grit in gutters. Filters choked, boil notices followed, and the choreography of daily life shifted to barrels and buckets and careful sips. Plants suffer first when sunlight thins. A film of ash keeps leaves from breathing, stomata clogged. Photosynthesis slowed, and midday feels dim even in noon's geometry. Yet soils remember these gifts differently. With time and rain, the same ash becomes a slow feast. Trace elements, minerals ground fine, a natural fertilizer that has built green countries from black fields again and again in human history. The story asks for patience. First you sweep roofs and paths, then you protect water. Then, in weeks and months, the gray loosens its hold and the green returns. Not all the ash fell back to familiar ground. Some grains and droplets climbed higher than the weather itself, lifted into the stratosphere where air is thin, clouds are rare, and the mixing with the world below is slow. The troposphere, where our day-to-day happens, trades air with the stratosphere reluctantly. So the smallest aerosols, sulfuric acid droplets, particles touched with hydrogen sulfide or hydrochloric acid, can linger aloft, circling the globe for months or more. Up there, they become mirrors more than blankets, scattering a small fraction of sunlight back to space and lending a faint, temporary coolness to the planet's skin. Eventually, gravity and weather lean them back down. When those same acids rejoin the troposphere, they return in raindrops, mild in many places, sharper nearby, an unwelcome cousin of ordinary showers that we simply call acid rain. The same veil that cools a little may sting when it comes home. There was another, stranger teacher in those satellite loops, the pressure pulse. In infrared, where even small temperature changes write their signatures, you could see it as a ring, a bright-edged ripple racing outward from the center of the blast. It spread across the Pacific like the wake of a continent-sized ship, then kept going, curving with the Earth's roundness, nudging clouds and bending winds. The wave moved at astonishing speed, close to what we call the speed of sound for long, shallow atmospheric swells, and it did not whisper. Along its path, people felt the world press very gently and then release, as if a giant had sighed. On one island, 65 kilometers away, the boom arrived like an invisible hammer. Recordings caught the single clean clap and the rush of air that followed. Farther off, reports told of windows blown out, panes flexed past their patience by a pressure step that no one could see. What makes a pulse like that so clean? Part is the geometry. A blast at the ocean's surface couples energy into the air as a nearly perfect ring. Part is the clarity of the higher air, which lets waves run long without shredding. Part is the scale of the source, which, for a brief instant, released power in a way our instruments rarely witness outside of tests and metaphors. When you watch the loop, each frame is a soft drum. Together, they form a rhythm. You can almost breathe to expand, fade, expand again, and somewhere between heartbeats, you realize you're watching sound write a circle on the sky. Under the canopy, the sea had its own ledger. Pressure jolts and falling ash can drive tsunamis and seas. The water sloshing in harbors and running up beaches in surges that look less like the tall walls from movies and more like a rapid, angry tide. Cables on the seafloor felt the blast as a pressure change rolling along the deep. Instruments on coasts far away traced curious fluctuations long after the sound had passed. For Tonga itself, the immediate dangers were simpler and sharper. Waves washing into villages, boats torn from moorings, low-lying strips of shore suddenly remapped by a gray, gritty line. There's a grief in such events that numbers can't tidy up. Ash in water tanks isn't just a chemical. It's morning tea delayed, babies' baths postponed, elders' routines broken. A field gone gray is not merely a problem of albedo. It's a family's cassava and taro waiting for rain strong enough to rinse leaves clean. And a sky that has lost its blue casts a mood that every child understands without learning the word aerosol. Yet there's also a knowledge that flows through communities used to living with islands that grow and vanish. You check on neighbors, you sweep together, you keep an eye on the horizon and an ear on the radio, and you store the lesson for the next time the sea decides to lift fire into air. Seen from far above, this is data and dynamics. Seen from the ground, it is breath and memory. The largest plume ever caught so clearly on camera became a global lesson in scales. From orbit, a flower the size of a subcontinent, a ring riding the air like a thrown stone circle on a pond. From an outer suburb, the sound arriving a minute late, a pressure wave that shakes the door. From a kitchen, ash dusting the step like the first snow you didn't ask for. All three are true at once. The eruption isn't an image, it's a choir of experiences that harmonize whether or not we are listening. If you could hold the whole story in your palm, you might keep a few pebbles for memory. Late December, the stirrings begin. January 14, a 20-kilometer column, immense from shore, a filament from space. January 15, a bloom caught by Goes West and Himawari 8, an ash canopy broad enough to drape across Europe, lightning inside counted beyond 200,000 by radio ears. Ash falls, islands go gray, water needs guarding, lungs need care. Later, soils accept the gift after the shock, leaves find green again. Aloft, aerosols mirror sunlight for a while, then return as a faint sting in rain. And after is always the same verb in another tense, to breathe. The volcano breathes, the atmosphere breathes, people do too. In the quiet, after the loudest minutes, there's a small gratitude, the ocean settling, roofs still holding, neighbors present. Scientists replay the loops, time the wavefronts, trace the lightning's birth, test the ash. Gardeners brush breadfruit and papaya leaves and wait for a storm that washes clean without washing away. When night folds in and the islands are dark coins on a silver sea, the plume fades to black, but the lesson stays bright enough to see without light. Beginnings can be gentle, endings enormous. A pin from orbit can be a wall from a canoe. A thunderstorm can be stone dust and torn seawater. A ring in the sky can rattle a window miles away. So, let the shoulders settle and the breath lengthen. The ocean will sleep again. The islands will green again. The world loud for a moment will return to its soft work of turning and mending. And while the sea grew calm, the air kept a record. Across the world, barometers felt it first, the lightest tap on the planet's skin. A rise and fall so slight most of us never noticed, though instruments did. The pressure wave from Hunga Tonga Hunga Hahapai lapped the globe again and again. At least 4 full circuits written as pale rings in weather data from the United States and far beyond. In kitchens and living rooms, nothing snapped. The wave was mostly below hearing there. Yet needles twitched, digital traces stepped up and down, small breaths passing over towns that had never heard the volcano's name. Elsewhere, it was audible. A deep, traveling sound reached New Zealand and Australia. Even Alaska, far thunder without a storm. The air remembering the shape of a sudden release. We usually teach ourselves that eruptions underwater don't raise great traveling walls of sea. The ocean tends to absorb, to swallow the blow and smooth it out, but scale can be its own physics. This explosion was so fast and so large that it pushed water hard enough to launch a tsunami, not the towering black-sided kind that lives in our fears, but a set of long, forceful surges that still had teeth. Across the Pacific, wherever coasts faced the source, gauges clicked into alarm, and harbors drew a breath they hadn't planned to take. The wave's personality changed as it neared land. The same energy that was low and flat in deep water rose into something you could see and measure near shore. A bulge that hurried in and then hurried back, repeating. Untidy, impatient. People who know the sea know what to do when that word travels. Boats slip their lines and nose outward. Far from shore, the passing swell is a broad hump, a lift and fall that a good bow can ride. It's the pinch near land, the shoaling, that turns a gentle step into a break that can batter docks and hulls. And so you could watch them on camera, bright specks heading for deeper water, choosing space over shelter, because in this kind of event, shelter becomes a trap. Near shore, the same wave looked big, almost theatrical, as if it had grown in minutes. That was an honest illusion born of physics. A long wave spreads its amplitude when the floor rises to meet it, raising what was subtle at sea into something with a line on the wall and a wet mark left behind. Beyond harbors and beaches, the eruption's last, and perhaps saddest, damage was to the volcano's own newborn body. Hunga Tonga Hunga Ha'apai was young enough to remember its first morning. It rose in 2014 from two low islands, separated by a flooded caldera about 150 meters below sea level. That gap filled with erupted ash and tephra, and for a while the sea withdrew. A narrow isthmus bound the siblings together, and a continuous rim looked out across a blue that had once occupied the volcano's mouth. You could walk it and feel the planet's patience and haste at once. A place made in weeks by forces that usually work in eras. The setting was always restless. The rim sits squarely on the meeting line of the Pacific Plate and the Indo-Australian Plate, a convergent boundary with the kind of underground conversation that never ends. It was exactly the sort of laboratory scientists love. Fresh land, known birth date, clear materials, ocean all around. NASA and other teams turned their attention there, not to claim or to tame, but to watch how water and volcanic debris negotiate a truce. Mars, after all, is still dotted with old volcanoes that likely saw water once. The planet's past may include shorelines and waves, deltas and bays. If you can watch a baby island in Earth's ocean weather its first years, you might see patterns that rhyme with the erosion etched into Martian calderas and lava plains. You can test whether wind and wave carve certain curves in predictable ways, whether ash hardens into something more resistant when the sea salts and rain acids pass through it, whether the first 6 months matter most. At first, the sea did what seas do to castles of powder. It came and took them back. The ash that had bridged the two older islands washed away in bites and slices. Gullies ran like chalk lines after rain, and the newborn neck looked vulnerable, as if a single storm could erase the map. Then something changed. Chemistry, time, and weather conspired in a quieter direction. Ash and seawater, grinding and reacting together, produced a rock harder than the loose grains that birthed it, a cemented skin more resistant to nibbling waves. Within about 6 months, the ferocious erosion slowed and then nearly stopped. The island might have lasted years, even decades, if the earth beneath had chosen sleep. It did not choose that. On January 15, the volcano reminded everyone that geology is a heartbeat, not a photograph. The force of the eruption rewrote the coastline in minutes. Aerial and satellite views after the event showed a gap where the neck had been. Ocean flooding into the caldera again. The continuous land now torn back into two separate islands facing each other across open water. The infant's face was different. The mouth had reopened. The sea reclaimed the space above the vent as naturally as breath reclaims a chest. The scale is easy to miss. From above it looks like a scratch in blue, but imagine the sea floor without water. What we call an island is the crown of a mountain. The lost neck sits atop a structure 2,000 meters tall from base to summit. A true volcano, whether or not a few meters of land show above the waves. If Earth were dry, as Mars appears, we would be standing at the foot of a massive cone, rather than squinting at a torn ring in a photograph. There is a comfort, strange as it sounds, tucked inside the ore. For all its size, for all the rings of pressure that ran the world and the plume that painted the sky, this explosion could have been crueler. Its timing, geometry, and the daily lives of people in its path combined to spare what might have been lost. That is not to minimize the real harm: flooded homes, fouled water, a landscape going gray, but to let the mind exhale. In a world with forces this large, we were lucky this time. The science does not close its book after the first chapter of astonishment. NASA's eyes will return to the islets and the gap between them, reading the new forms as they evolve. Each storm that passes, each swell that brushes the ash-steep slopes, each rain that carries salt deeper into the welded layers adds a line to the story. From orbit, you can measure area and color. From spectrometers, you can learn about minerals and glass, about how quickly a fragile crust becomes a tougher stone. The seafloor around the caldera has its own story, written in sonar. Blocks shifted, sediments moved, an underwater apron thrown outward by the blast. All of these details build a dictionary you can take to other planets where the words have faded, but the syntax remains. On Mars, for instance, you can trace terraces that look like wave cuts. You can find tephra hardened into paler, tougher strata. You can read collapses around calderas that mirror shapes on Earth. The closer you listen here, the more fluently you can listen there. Why should anyone far from Tonga care about this grammar of ash and sea? Because the air we share is a single room, and because the ocean is a single bowl with many shelves. An eruption of this scale teaches us how energy moves through the atmosphere, how pressure waves propagate, how they couple into tides and currents, how aerosols loft and linger, then descend. It shows us how quickly harbors must decide, how communication between islands and ships and weather offices becomes the roof over a community's head. It gives forecasters new toys that are not toys at all, better ways to see shock fronts, to model the growth and collapse of plumes, to estimate lightning hazard in volcanic clouds where ordinary intuition fails. And on a longer arc, it lets climate modelers compare expectations to reality. How much shortwave light is bounced by sulfuric aerosols? How the small global cooling that follows compares to past events? How long the veil remains before it thins and falls as sour threads of rain? There is also the old reason, the human one. Catastrophe and wonder often arrive together, and part of caring is learning to hold them both without letting either bruise the other. In Tonga, people swept ash from roofs with laughter they made on purpose, because laughter steals weight from the arms. They shared water, checked on elders, cleared roads with shovels and bare feet, and they listened for the next advisory the way you listen for a friend climbing the stairs. Somewhere else, a child watched the satellite loop and decided to become a scientist. Somewhere else, a retiree took out an old barometer and saw the tick that proved the wave had passed. The planet had used its outdoor voice, and the echo had been caught by instruments and memories alike. The wave that circled the world 4 times owes part of its endurance to the air's layers. High above our rooftops, the atmosphere is a set of stacked lakes, each with its own currents and habits. A strong blast couples a pulse across those surfaces, letting it circle like a runner who needs only a gentle push to keep going. In the records, you can see the arrival's first crest, then another hours later, then again after a sleep, like notes from a drum you forgot you were playing. Most of us felt none of it. A few of us heard it as a low roll. Nearly all of us saw its sign once someone pointed the camera and overlaid the line. It is humbling to learn that the air can carry a memory so far, so faithfully, with so little drama, just the world's softest finger tapping at a needle 4 times in a day. If you return your gaze to the island itself, there's a different lesson in patience. The place is not gone, it is rearranged. The 2 higher blocks remain, guardians of a gate the sea now owns again. Between them, the caldera breathes, sometimes as steam through new vents, sometimes as silence. With time, more ash will settle, and new crusts will try to knit across the gap. Storms will try to gnaw them back. Occasionally, the volcano will build another neck and the map will change, as if someone kept retying a ribbon and watching it come undone. Each tying and untying teaches the sea and the land how to talk to each other, and we learn by eavesdropping. Think, too, of the mountain hidden by the water. If the Pacific were to drain the way a bathtub does an image, both fanciful and useful, you would see the full relief. Flanks streaked with old flows, terraces where slumps paused, a summit ring that frames the throat. 2,000 meters of height is not a toy. It would dwarf the skyline of most cities and place snow where now there is spray. Seeing that in the mind makes the words small island feel small in your mouth. What we stand on is often only the part a wave can't quite reach. So we fold this event where it belongs, near the front of the shelf, where the things we most want to remember are easy to touch. The pressure wave that lapped the earth 4 times. The tsunami that was not large but was large enough. The boats that went outward to meet a wave rather than waiting for it to crowd the dock. The newborn island that proved ash and seawater can make a tougher stone, given months and calm. The same island split, its neck torn by a blast that erased a year's work in seconds. The quiet knowledge that we were spared a worse version of the day, and the promise that NASA and others will keep watching, because the way this place erodes and heals can help us read Mars, and more quietly, read home. When the loops stop playing and the headlines cool, the volcano will keep doing what volcanoes do, storing and releasing, dressing and undressing its rim, inviting the sea to argue and agree. The world will keep measuring with careful tools and with ordinary hearts, barometers and buckets, spectrometers and sweep brooms, models and memory. And somewhere, when one more pressure ring passes a weather station in the night, a small printout will record a shift that looks like nothing and is, in fact, a planet speaking in a very soft voice. If you listen now, in this dim room, you can almost hear it, the echo at the edge of hearing, the hush of a wave that has already gone by, the sense that we live on a world that can be loud and kind in the same afternoon, and that our work, as ever, is to learn its language well enough to be good neighbors to the sea, the air, and to one another. Hold this small world in the palm of your mind and feel how quiet it appears at first. Just a white bead, 6th in size, among Saturn's many companions, drifting where the light is thin and the cold is patient. In natural light it doesn't shout, it glows. Enceladus wears a cloak, the color of snow pressed smooth by dawn-clean ice, with almost nothing else mixed in, and the sun glances off it so efficiently that the surface keeps its chill, noon lingering near 200 degrees below zero. That high reflectivity is its own lullaby, a bond albedo close to 0.81, as if the moon were a mirror, taught to return most of what touches it. You'd be forgiven for thinking not much happens on a place so pale. But if you wait a breath and listen, you'll hear the faintest hiss at the south, like steam through a seam in a kettle. The ice is not silent. Jets of water vapor rise from the moon's underside, thin feathers against space, a sign that under the frost, a sea is awake. It helps to place Enceladus gently in its neighborhood before leaning toward the sound. Around Saturn orbits a family so numerous we learn their names in handfuls, and new crumbs of ice in the rings blur the line between moon and moonlet. Enceladus is the 14th closest we currently count, and the 2nd closest major moon tucked just beyond the main rings, on a path that lies almost exactly in their plane. It loops Saturn in roughly 33 hours, a quick day and night for a body that small, and it keeps company with Dione in a rhythm that matters. a 2-to-1 resonance. 2 laps of Enceladus for every lap of Dione. That resonance refuses to let the orbit turn perfectly round. It leaves just enough oval in the path for tides to knead the interior. A world can be warmed without ever seeing a summer if another world keeps time with it closely enough. Look again at the skin. Because almost nothing but water ice coats the surface, Enceladus is among the whitest things the sun touches. The whiteness isn't decoration. It's a working part of the place. Light comes in, light goes out, and very little heat stays. The crust hardens in that brilliance, and darkness, ice on ice, blankets on blankets, and yet, 30 to 40 kilometers down, pressure and tidal work change the story. There, beneath the shining shell, the water forgets how to be ice. Tidal deformation, tiny flexes driven by that not quite circular orbit, turns motion into warmth. Ice close to fractures warms enough to soften, and softened ice melts, and meltwater gathers, and soon you have not a pocket but perhaps a mantle of liquid, maybe even a global ocean with the crust as a floating lid. At the least, under the South Pole, the evidence stacks like smooth stones. A sea sits nearby, pushing gently upward against beams that creak. We don't have to imagine those beams alone. A spacecraft we sent with patience and grace circled this system for years. And in the long blue of Saturn's shadow, it kept its eyes open. Cassini was our lantern. It watched Enceladus in exquisite detail, sometimes brushing the plume so closely that ice grains peppered its skin, sometimes tasting the breath itself with instruments that could weigh a molecule and hear a salt. From Cassini we learned the habit of the jets. Always the south, always from long cracks, we began to call tiger stripes. Always rhythm in their strength, stronger at certain points in the orbit, weaker at others, as if the moon were breathing a tide. From Cassini, we learned that the gas is mostly water vapor, and that the grains carry salts and a dusting of organics, the kind of faint, basic chemistry you expect when liquid water has met stone in the dark. Let your gaze move toward the ring that is hardest to see. Saturn wears many rings, some bright and near, some parts of a larger veil. The E-ring is a ghost ring, a wide, diffuse halo that is clearest when backlit. Enceladus feeds it. Those southern jets fling water at speeds that would feel like a storm to a person, 2,000 kilometers an hour and sometimes more, and the moon's weak gravity cannot keep most of it. The plume throws grains and vapor into Saturn's realm. Some escape, some circle back, and many are captured into paths that together make the E-ring. You could say Enceladus is writing on the darkness with its own breath, and the writing stretches millions of kilometers. All of that from a moon the color of a snowdrift. The contrast is almost tender. On top, a surface so young and clean that craters are erased by geology that works in ice, not stone. Enceladus wears plains of dazzling smoothness, banded terrains where the crust has been pulled and stitched, ridges and troughs like the fine pleats of a garment. At the south, 4 long chasms parallel, deep and gently glowing in thermal images, cut the cap into stripes. You can trace their names with your finger if you like, but better to feel what they are. Cracks where the lid is thin and the sea finds sky. Cassini saw heat along those lines, enough above background to declare warmth in the language of a sensor, and it watched how the glow changed with where Enceladus was on its path around Saturn. The closer the moon came to a particular tug, the more the cracks opened. The farther it drifted, the more they rested. Tide and vent. Inhale, exhale. Numbers, when placed softly, help keep the story from floating away. 33 hours for an orbit, a 2-to-1 resonance with Dione, an albedo, near 0.81. Noon surface temperatures around 200 degrees Celsius. A shell perhaps 30 to 40 kilometers thick, with liquid below. Jets that loft on the order of 250 kilograms of water per second. Grains and vapor together, molecules and ice clumps, each on a ballistic arc to a ring or a fallback frost. These are not the clatter of a lecture. They're the small weights you tuck into a pocket so the wind doesn't carry you. Hold them and the images have context. The cliff edges, the faint fog, the bright stripes. Out beyond the numbers are the textures that make the science feel close. The plume doesn't roar, it whispers in streams. Hundreds of thin fountains layered into fans. In some frames, the sunlight catches the spray, and the seam looks like a soft white beard against the black. In others, it is only a glow in infrared, a warmth measured in milliwatts per square meter, yet unmistakable against the cold. Cassini's cameras saw curtains and filaments, the way a waterfall becomes lace when it falls from high enough and fine enough. Instruments that sniffed the plume reported salts, sodium, and potassium traces of carbon-bearing molecules, the suggestion of tiny silica grains, like those made when hot water meets rock at pressure. All of these together point to a particular kind of kitchen beneath the ice. Liquid water touching a rocky core, exchanging heat and taste, perhaps even making habitats where chemistry can take its time. Where does the heat come from? And why does it keep coming? The answer is mostly in the timing. If you could press your ear to Enceladus's orbit, you'd hear that it never hums a perfectly round note. The resonance with Dione holds a small eccentricity in place, preventing the path from relaxing into a circle. Each lap brings stretches and squeezes. Inside, the rock skeleton flexes. Friction in those flexes turns motion into warmth. Some of that warmth melts, some of it softens, and the softened places become conduits. It's a quiet engine, both delicate and durable. No vast furnaces, no deep magma seas, just tides, converted to enough heat to keep an ocean from freezing, solid under a lid that would otherwise seal it forever. Because the surface is mostly clean ice, light does a particular dance there. Sunlight glances off with minimal absorption, and the shadows are clear, gentle-edged, like pencil marks on paper. You can measure the whiteness across the spectrum and find that Enceladus reflects almost everything offered, which is why it stays so cold on top. That same cold means the frost that falls from the plume's breath can settle and shine, renewing the glare over time. In places where tectonic work has tugged fields into stripes, you see contrasts. Fresh, bright stretches against slightly older, slightly grayer bands. A record not of impact, but of internal motion. Look once more at the South Pole. The tiger stripes are not just lines, they're living boundaries between the undersea and space. Each crack, likely on the order of hundreds of meters wide and deeper than any mountain is tall, is a path where pressure is relieved in a graceful way. Vapor lifts, ice grains ride the rush, and the vent's rim cools even as it guides hotter water below. Cassini found that the power coming from the South Pole region dwarfs the simple expectation from sunlight alone, a sustained output that tells of a source deeper than weather. When the moon is closer to the part of its orbit where tides pull more, the cracks gape a bit and the jets brighten. As it moves away, they ease toward a calmer state. A moon breathing on a schedule set by gravity's clock. You might wonder how sure we can be of liquid water when we never saw an ocean directly. The answer is a braid of clues. There are the plumes themselves, water in both vapor and ice. There are the salts and trace compounds, The silica hints. There's the way Enceladus wobbles a little as it turns, a libration measurable by careful watching, consistent with a shell not anchored tightly to the core, but floating an ice lid over a decoupling sea. There's the gravitational field, mapped by tiny changes in the spacecraft's speed during flybys, which points to densities and shapes inside that match a global ocean better than a handful of isolated lakes. None of these is a photograph of a wave. Together, they are a portrait of a sea. Some nights the mind drifts from a moon to the ring it feeds and back again, because the system acts like a single instrument. The plume writes the E-ring. The ring showers grains back in faint, slow drifts. The grains fall, altering the surface reflectivity. The bright surface keeps the top cold and the bottom relatively warm by contrast. The cracks open and close with tide and throw more spray. A loop of cause and effect, gentle and persistent, plays across years. If you were to stand at Enceladus's south pole, in imagination and many layers, you might see against black space a fine, glinting haze arcing up and away, and know that some part of it will join the ring that arcs overhead like a whisper, and that some part will snow back down, renewing the very ground beneath your boots. Hold Enceladus a little longer before sleep. It is small and very far, yet its story reaches the warm part of the chest because it blends simplicity with wonder. A white surface, very cold, a not perfectly round path, kept so by a neighbor's timing, the slow work of tides turning to heat, and under the crust, liquid water touching rock. From that modest recipe comes an ocean that blows through its own ceiling, a ghostly ring around a giant planet, and a place where we can practice the question we always carry into the dark. Could life find a way to be comfortable here? No promise is made, only possibilities. But possibilities are enough to keep a watch. Cassini gave us the first long look and the first taste. Future travelers may swim the plume again, or slip a probe through a crack in the lid, or lower an ear to the ice and listen for the sea. For now, it is enough to know that Enceladus is not only beautiful, it is active in a way that makes the night feel friendly. Water vapor jets from its southern hemisphere, about 250 kilograms each second, on average fast enough that much of it escapes, generous enough to build a ring. The orbit fits into Saturn's pattern with precision, 33 hours per turn, aligned with the rings like a bead slipping along a thread. The resonance with Dione keeps the dance from settling, and the dance keeps the ocean warm. The ice is the brightest white we know, and the world beneath it is the darkest blue we can imagine. If you let your shoulders drop and your breath slow to match the moon's long exhale, you can almost sense the plume's fine spray on your cheek, cold and clean, a reminder that even in the far reaches, under a sky pale with rings, water is moving, and the universe is humming a soft song about home. Seen from the right slant of sunlight, the ring fed by Enceladus turns a color that feels more temperature than hue, a blue so cool and even that it seems to breathe. The grains there are tiny, uniform, and the light threads through them like morning through mist. From that patient scattering the E-ring earns a quiet superlative, the bluest thing in the solar system. Bluer even than Neptune, because the ring's texture is so consistently fine. Hold that image for a moment. A wide, soft band, the second outermost of Saturn's rings stretching for thousands of kilometers, yet so diaphanous that you only truly see it when the sun is behind it. When backlight turns dust to silk, its stated breadth is a modest figure about 2,000 kilometers in the simple telling, but the way it spills outward with faint edges makes numbers feel like the wrong kind of net. Better to say it is a ghost river wandering the planet's dusk. Enceladus draws the ring's shape the way a skater draws arcs on fresh ice. As the moon circles Saturn, its south pole fountains flicker in strength with the tide, and each burst lays a filament into the E-ring. Cassini caught these as tendrils curling, braided wisps that bloom near Enceladus's orbital longitude. More material added when the moon exhales strongly, less when the seams quiet for a while. Then, as Enceladus moves on, the ring remembers it was once smoother. Collisions between grains, faint electric whispers, and gravity's constant nudge all work the tendrils back toward a gentler curve. What looks like calligraphy one week fades toward plain script the next, until the next strong breath writes again. If you imagine the ring as a lace scarf, Enceladus is the hand that every so often tugs one corner and leaves a temporary, flowing crease. The most intimate readings of that crease came from a spacecraft built to be curious in general and nimble in particular. Cassini was never meant to sip an ocean's spray. When it left Earth, no one had seen the South Pole plumes. Yet on board was a small, exquisite listener, the cosmic dust analyzer designed to catch and weigh the tiniest grains wandering Saturn's neighborhood. When the fountains were revealed, engineers and scientists turned that ear toward the moon's breath. On some passes, Cassini even flew through the plume, letting grains tap its skin and instruments taste what they could. It wasn't a perfect spoon for the soup, it was made for ring dust, not fresh ocean breath, so we speak with care about full pictures. But even an imperfect spoon can tell you if the broth is salt or sweet. Water, unsurprisingly, sang the loudest. The plume is mostly this: vapor and ice, hurled into space and lit from behind, falling back as frost or sailing into the ring. But the dust analyzer and other instruments reading mass and light in their different ways found more than cold water. They saw the signatures of carbon dioxide and nitrogen, of methane, and hints of organic complexity that feel like the first phrases of a longer sentence. Among the more evocative whispers were the amino acid-like signals folded into grains, the very kinds of building blocks we know gather around deep-sea vents on Earth. None of this constitutes a promise. It is not a photograph of a cell. It is, instead, a scent carried on steam, molecules that, in our experience, like to live where hot water meets rock and time is generous. That image invites a gentler question than the headlines ask. Not, is there life? A question that tries to jump the river in a single leap, but what kind of kitchen is down there? On Earth, where a mid-ocean ridge cracks open and water curls into the crust, hydrothermal vents build chimneys of mineral and exhale chemistry rich in energy. Around those chimneys, bacteria and archaea and then entire food webs take root, feeding not on sunlight but on the redox feast served from inside the planet. On Enceladus, the recipe could rhyme: a liquid ocean, an interface with something rocky, heat from tides, water circulating through pores and fractures, minerals leaching into solution, gradients to climb. If such vents exist beneath the ice, the plume is their gossip salts, traces of carbon-bearing molecules, perhaps amino acids wafting up through cracks to frost the sky. But kitchens presume counters and stoves, and that turns our eyes inward to the structure of the moon itself. For a while, some imagined Enceladus as a near-solid pearl of water frozen through, a simple bead with a skin. Cassini, however, weighed and watched with the kind of attention only a long mission grants, and its gravity readings, its tracking of a subtle wobble, and its plume chemistry wove a different picture. The mass is a touch larger than water alone would suggest. The way the crust rides tells of decoupling from beneath. The clues point toward differentiation, the interior separated into layers instead of being a single blend. In this telling, Enceladus owns a rocky and perhaps iron-salted core, an ocean above it, then the ice lid that dazzles our eyes. Differentiation is a quiet word that means a body had enough warmth and time to let heavy things settle and light things rise, to become a world with rooms rather than a single undivided hall. It's worth pausing on scale, because scale brings humility. Enceladus is small, roughly 500 kilometers across, about the distance of a long day's drive, so small that it sits on the border of what we call hydrostatic equilibrium. That phrase is simply a promise that gravity has rounded you, made you a sphere or something close, pressing mountains down, letting basins fill. Some objects this size don't quite make it. Neptune's Proteus, for instance, keeps its blocky outline, a relic of insufficient self-gravity to sand the corners down. That Enceladus wears a smooth shape at all tells you something about its past, and that it might be layered says more. Even small worlds can be organized when their histories include warmth, collision, and time enough to settle. Assume, then, a differentiated interior for this small white bead. The core is mostly rock silicates with a seasoning of iron, and it is there, at stone's exposed surfaces, that ocean water can pick up more than chill. Rocks give. They leach sodium and potassium, silica and other traces. If reactions between water and rock are exothermic enough, if pores are wide and circulation is brisk, if pressure and temperature find their sweet spot, then hydrothermal systems can persist, opening microscopic caverns where complex molecules assemble and reassemble like beads on a string. When Cassini's instruments reported not just water, but carbon dioxide and methane, not just light organics, but the possibility of amino acid-bearing grains, it nudged the picture toward this rock-water conversation. Circle back to the ring the bluest, the softest, because it is both product and proof. Every second or so, a few hundred kilograms of water rush through the tiger stripes and become sky. Some grains are so small that blue light bends and dances among them longer. That is part of the ring's color magic. Some vapor escapes Enceladus entirely and then meets Saturn's broader realm. Some falls back like tender snow. The tendrils that Cassini watched, newly added filaments in the ring, tell you when the ocean is breathing a little harder, when the cracks have opened a little wider. Later, as the moon moves to a quieter stretch of its orbit, those same filaments blur into the ring's evenness, like ripples relaxing on a lake at dusk. There is a human warmth to the way we learned these cold facts. A machine, built before the plume was known, ended up flying through it. An instrument designed for general dust-sniffed ocean spray. Observers expecting quiet found a moon that writes lace into a ring. The mission stretched long enough that scientists could watch rhythms instead of snapshots, vent strength, waxing and waning with orbital position, faint changes, carving recurving art into the E-ring, the South Pole glowing steady in infrared, while the rest of the skin glittered with frost. None of this would have been visible if Enceladus were not so white. That very brightness, reflecting sunlight away, kept the surface cold enough to store contrast for our cameras and deepened the shadows that let us see. We often think of worlds as places that must be grand to matter. But Enceladus argues softly for the opposite. Small, nearly at the threshold of roundness, it nonetheless holds a layered interior, an ocean, and behavior that spills into the architecture of a giant planet's rings. The borderline nature of its hydrostatic equilibrium, so close to being too small to become a sphere, makes its apparent differentiation more wondrous, not less. It is as if a snow globe learned, in its modest gravity, how to arrange its heart and write its weather in a halo hundreds of thousands of kilometers wide. And beneath the tenderness of the ring's blue is a set of questions we can carry without exhausting ourselves. How deep is the ocean, really? And how salty? How porous is the core? And how hot are the vents, if vents there are? Do amino acids in the grains mean assembly lines below? Or are they the products of simple chemistry in cracks near the surface? What governs the timing of the tendrils? Beyond the first-order tide, does the ring feed back on the moon, ever so slightly, with charged grain and field? None of these questions demands a shout for an answer. They invite what Enceladus invites in general: to watch longer, to listen closer, to let a small world teach scale by example. So keep the essentials, like smooth stones, in your pocket. The E-ring, second outermost, made visible most beautifully by backlight. Its apparent 2,000-kilometer breadth, only a doorway into a much wider veil. The ring's blueness, born from fine, uniform grains scattered from a South Pole ocean's breadth. Tendrils, etched by Enceladus's orbit, smoothed as the moon moves on. Cassini's unplanned tastings, water predominant, yes, and also carbon dioxide, nitrogen, methane, and amino acid-like signatures that make the heart lean toward hydrothermal scenes. The inward picture, adjusting with gravity's ledger, a mass that argues for rock at the center, a differentiation that lets an ocean sit above a core. The reminder that 500 kilometers can be enough for roundness, enough for layers, enough for tides to make warmth where sunlight cannot. If you rest your head now and let the room's quiet return, you can almost see the ring as a pale scarf around Saturn's shoulders, its blue deepening where the sun shines through, its weave occasionally puckered by a tug from a little moon below. Somewhere under that moon's ice, water moves through stone and comes back changed, carrying traces of its journey into the open. Space is cold, Enceladus is colder still, and yet, in that cold, a kind of gentle weather persists. Steam rising in a vacuum, frost falling on a mirror, a ribbon of blue drawn so delicately that it feels like a promise rather than a fact. Thermal activity isn't a rumor here. It's the quiet engine that keeps the moon breathing. You can see it in the way the South Pole exhales plumes rising in thin, sparkling veils, and you can feel it in the maps Cassini drew in heat instead of color. As the spacecraft glided over Enceladus again and again, it stitched together a portrait of warmth along 4 dark seams that circle the south like parallel scars. We call them tiger stripes, but the name doesn't capture their scale. Each is roughly 130 kilometers long, about 2 kilometers wide, and half a kilometer deep, tectonic fractures in the ice that serve as doors between ocean and sky. The jets don't wander. They line up with these chasms as faithfully as breath lines up with a mouth. Where the stripes are, the vents are. Where the vents are, the surface glows in infrared, a soft ember against the world's general chill. What's most startling, once your eyes adjust, is how young the South looks. Impact craters, those patient circular stamps of time, are almost absent over the southern hemisphere, and even elsewhere, they're fewer than your intuition expects for a world so old. Enceladus carries only a whisper of atmosphere, a thin veil of water vapor, sourced by its own plumes. It's far too slight to burn up incoming stones. If meteoroids come, they should land. The reason they leave so little trace is that the surface doesn't keep scars for long. Frost falls out of the plume and drifts down like a snow that never quite ends. Warm ice flows a little, then refreezes. Fractures open and close. Over years and centuries, small dents soften, edges blur, and what was rough becomes a smooth page again. Rounding, for such a small body, isn't only gravity's work. It's also the moon's habit of laying down fresh sheets of ice. Apart from the tiger stripes and a scattered handful of craters, the relief is modest. You won't find proud mountain chains marching from horizon to horizon. No jagged massifs shouldering into the sky. The topography changes in a quieter grammar. Low rises and shallow swales, wrinkled belts of ridges where ice was pulled and pushed, collapsed pits here and there, and long corrugations like pleats pressed into satin. Near the South Pole, if you zoom your mind's eye down to the highest resolution frames Cassini sent, the ground looks almost terrestrial for a moment. A giant glacier with both satin-smooth runways and fields of jagged, blocky chaos. Even in a single view, you can read two tempos, surfaces ironed flat by deposition and flow, and nearby zones where slabs have broken, tilted, and been shoved together like ice floes trapped by a tightening wind. Travel north in thought, and the mood changes. The North Pole tells its age by counting. Craters punctuate the plains in a way the South refuses. There are fractures here, too, the moon is laced with them, but no plumes rise from these latitudes. No constant fall of frosty ash to renew the paint. Without that gentle, ongoing resurfacing, the North keeps a ledger of impacts across long eras. The contrast itself becomes evidence. One hemisphere constantly refreshed by cryovolcanic breath, the other more stoic, letting the cosmos leave its small, round footprints. It's like walking from a fresh snowfall into a field that hasn't seen winter yet. The difference is not a mystery, but a narrative. When Cassini crossed low over the South, it didn't just taste the plume. It lingered on the ground with a close, careful gaze. The areas near the tiger stripes look as if the crust has been folded, buckled, and needed ice, behaving like rock would at great depth, or like taffy under a steady pull. You see long, nearly parallel troughs with steep, clean walls and darker floors. You see bands of finely ridged terrain that run like cords alongside the main fractures. You see suture textures, where two surfaces have slid past each other and frozen into a new fit. It's unfamiliar and intimate at once, a landscape drawn in the lines of strain, where the ocean's pressure and the tide's timing have left their signatures in geometry. That we have such views at all feels like a small miracle of patience and luck. Cassini was an artist of long tenure, looping Saturn for years, until it knew every family member by their habits. To fly so near, to thread through a plume, to map heat along a crack in the ice from hundreds of millions of miles away, these are the kinds of close looks that come from mission teams choosing courage and care together. The spacecraft is gone now, folded into Saturn's air to keep its metal from ever troubling these clean worlds. With Cassini's finale, our eyes left Saturn's neighborhood. We have no sentinel in that sky today. We live, for now, on stored light. Images and spectra, gravity traces and dust counts, all the souvenirs a careful traveler can bring. Proposals have come and gone like comets, bright, convincing, then lost to other needs. A probe to fly through the plume with a better nose. A lander to set down near a stripe. A meltson to sip the ocean itself. a tiny swimmer to ride a vent's updraft. Each has been drawn on paper, in rooms where the night was full of rings and ice. They are not fairy stories. They are hard questions about budgets and power and time. One mission we do have is Dragonfly, a rotorcraft bound for Titan, the thick-aired, methane-weathered sibling that keeps its own secrets under an orange sky. Dragonfly will write a different book on another table. Enceladus will wait in its white quiet, with a couple of new mission ideas under review and the sobering arithmetic that even the best timelines often say years and decades in their margins. Waiting isn't empty, though. The data we have keeps deepening as we ask it better questions. Cassini's thermal maps tie the jets to the tiger stripes with a precision that makes the case for tectonic fractures robust. The plume's chemistry keeps nudging our models toward a rocky core, actively meeting water, because amino acid-like signatures make more sense in a kitchen with counters than in a pantry of pure ice. The absence of craters in the south is not just a look, it's a clock, keeping time since the last resurfacing. And the roundness of the whole moon, unusually smooth for something only about 500 kilometers wide, whispers that ice can carry a world toward equilibrium when it's constantly healed. Think of the interior as a layered lullaby, rock and perhaps iron at the center. Above it, a global ocean, or at least a vast southern sea. Above that, 30 to 40 kilometers of ice that flexes, cracks, and speaks. The tiger stripes are the lyric's 4 repeating lines, each hundreds of meters deep, that lengthen and shorten as the moon moves in its not quite round path. When Enceladus is pulled a little harder, the fractures gape and the jets brighten. When the pull eases, the gates relax and the breath softens. Cassini could see this rhythm in heat, in plume brightness, and in the ring-sculpting tendrils that trailed the moon along its track. A timetable written in gravity and frost. Weigh the surface again in your mind's hand. Minimal relief, few highlands, no lofty ranges casting dusk for hours. Instead, a language of lines and sheets. Where the crust has been folded, squashed, and shifted, you can read the forces at work. Compression knits ridges, extension opens troughs, shear draws chevrons like herringbone in ice. In some places, plates have collided softly and ridden up over one another, making low, blocky ramparts. In others, they've pulled apart just enough to reveal darkness below, all the way down to vents that coat their rims in frost as water vapor flashes and freezes. The nearest earthly analogues are places where glaciers fracture over uneven ground, or where sea ice grinds under wind and tide. But on Enceladus, the scale and regularity are different, set by a deep ocean and a global clock rather than a single valley or bay. The north remains the archive. Without plumes to snow quiet the ground, time is able to collect its circles in peace. The result is a balance. One pole is an active workshop, fresh shavings of ice, forever falling. The other is a library, shelves of craters spaced by chance and patience. Each tells the truth about the same moon from a different decade of its life. And between them, in the mid-latitudes, you find transitions, terrains with both crater ghosts and fresh fractures, a mixed grammar of old and new. If you let your attention drift to the wider family, you might feel a gentle tug from a farther, darker place. Beyond Saturn, past the frosted quiet where Enceladus writes lace into the E-ring, there is a moon that once revealed itself for only a few hours and then went back to living at the edge of our reach. It circles Neptune, backward and strange, with geysers that write black snow across pale plains. Its name is Triton. We met it in a single flyby, long ago in 1989, when Voyager 2 looked over its shoulder on the way out and caught sight of an object that did not fit any familiar box. The memory has waited patiently while our attention learned how to see small white worlds breathing at Saturn. In the same spirit, hushed, curious, unhurried, we can let that far visitor step closer, not with a jolt or a headline, but the way a new star appears when your eyes grow used to the dark. Imagine a far, cold evening where the wind is only the thinnest whisper and a pale disk hangs over an indigo horizon. Not enormous, not small, simply right, like the moon would look from a winter field at home. That disk could be Triton, if you were standing on the clouds of Neptune and looking up. We have not stood there. We only passed by once, in the summer of 1989, when Voyager 2 tipped its camera and gave us a few hours of attention on a world that had waited in the outskirts for billions of years. The pictures were few, the encounter brief, but the impression lingers. Triton is quiet in color and loud in strangeness, a moon that keeps the rules of orbits, only to bend them in new ways. Place it gently in its family first. Neptune holds 14 known moons. The inner ones are regular, calm companions moving nearly in the planet's equatorial plane, with orbits so close to circular that their paths read like compass-drawn rings. Past those steady beads, the story tilts. Triton is the first of the irregulars, and the word fits like a loose coat. Irregular means the orbit is inclined, eccentric, or backward. Triton's path is the most dramatic version of that last choice. As Neptune spins one way, Triton travels the other, circling clockwise around a planet whose own rotation is counterclockwise. The orbit is tipped steeply, about 130 degrees, with respect to Neptune's equatorial plane, so the moon's track scythes across the sky at a bold angle. And yet, for all that tilt and rebellion, the orbit's shape is nearly a perfect circle. Its eccentricity is close to zero. It is the direction, not the roundness, that breaks the pattern. Every other large, spherical moon we know goes with the flow of its planet's spin. Triton alone goes against it. That difference is a signature, a soft stamp that says, "I was not born here." The simplest reading is capture. Once upon a colder time, Triton likely wandered the Kuiper Belt out, where Pluto and 1,000 smaller worlds trace long, dim ellipses, until Neptune's gravity made an offer the moon could not refuse. Capture requires a trick. An object flying by must lose enough energy to stay, or it will simply arc past and be gone. The leading idea is a binary origin, the way Pluto dances with Charon. In that story, Triton came with a smaller partner. Neptune's pull unraveled the pair, flinging the companion away on a new path, while robbing Triton of the momentum it needed to escape. The larger body fell into Neptune's keeping, backward and inclined, with an almost circular track as tides and time rounded out the roughness. Scale helps the picture settle. Of the 14 moons we count around Neptune, Triton holds about 99.5% of the total mass, the way a big stone holds the weight in a bowl full of pebbles. It is the 7th largest moon in the solar system, smaller than Earth's moon, but large enough and near enough that, from Neptune's sky, it would look about the same size our moon does to us. More quietly, Triton is larger than Pluto. For years we spoke of Pluto as a king of the Kuiper Belt, but kingship is a perspective. Triton may well be a dethroned ruler, a Kuiper Belt body recast as a satellite by a meeting with a giant. When New Horizons swept past Pluto in 2015, its measurements suggested that Pluto and Triton share a near-twin chemistry: nitrogen ice on the surface, water ice beneath, carbon dioxide and methane frost in patches, strengthening the shared origin story with a gentle nod. Beyond Triton, Neptune's outer irregulars live on wide, elongated paths that take years or decades to complete. They are almost certainly captured, two dark crumbs that the giant planet gathered from the same deep pantry. Their orbits are odd enough that Triton's arrival may have disturbed them, stirring the outer shelves when the big newcomer came in backward and bold. Picture a quiet pond, and then a heavy stone tossed in from the side. The ripples rearrange floating leaves that were drifting in placid circles. Gravity does that, only without sound. Tilt your eye downward now, from orbit to skin. Voyager 2's brief look told a simple story in soft colors. The surface is mostly nitrogen ice, with water and carbon dioxide ices mixed in, a pale crust that glows with clean coal. The terrain is surprisingly even. Triton's topography varies by less than a kilometer across broad stretches. You find plains and plateaus, long troughs and low ridges, but not great mountain ranges. The photographs carried a second surprise, a lack of craters. Not none at all, but few, far fewer than a surface this old would collect if it simply sat and waited for the sky to write on it. Lack of craters means youth. Something has been at work, resurfacing the plains, smoothing and frosting and laying down new sheets over old scars. Parts of Triton, in Voyager's gaze, look like ice fields scoured and renewed. In other parts, reddish stains stretched across the pale tones patches, where methane has been altered by sunlight into complex organics called tholins, the tarry products of patient radiation and chemistry. Organic in this sense doesn't mean living, it means carbon-bearing, the sort of molecules that can serve as syllables in life's long sentence if the grammar liquid, energy, time ever allows. The air, thin as conscience, was there too. Voyager found a delicate atmosphere made mostly of nitrogen, with a hint of wind that moved bright clouds a few kilometers above the ground. The breeze was enough to shape frost and carry fine particles to sand surfaces smooth and lay veils over valleys. These details sound quiet, but they hint at warmth beneath the cold. To renew a surface, you must move material. To move material, you must have energy, internal heat, tides, or a coupling to a changing Sunday. Triton gives off a suspicion of that underground work in another way: geysers. They don't roar like earthly geysers. On Triton, sunlight can warm a thin, transparent sheet of nitrogen ice above a darker substrate. Gas builds in the space between, pressure rises, and the sheet vents sending a narrow plume, blackened by entrained dust, a few kilometers into the air. Voyager 2 caught a handful of these, wind-blown curtains, streaks trailing downwind for tens of kilometers, thin soot falling back and drawing ink lines across white paper. The mechanism we favor is a kind of solid-state greenhouse, gentle compared to magma, but effective. In the broader sense, it means the surface is active. A world that vents even in whispering plumes does not sleep. Return to the orbit for a moment, because direction matters to destiny. Retrograde motion makes Triton's long-term future fairly sure. It is spiraling inward, losing orbital energy to tides raised on Neptune, dropping bit by bit toward a limit where it will either break into a new ring or be torn apart and then gathered into arcs that outline the sky like a slow-motion crown. Not soon, long after our calendars are dust. But the tide is a patient accountant. It keeps records beyond our lifetimes. That inward drift may be one reason the orbit is almost perfectly circular now, energy being not only lost, but smoothed, eccentricity rubbed away by the same tides that nudge the moon closer. Composition ties the capture story to the skin you can see. Nitrogen ice is the primary paint. Water ice is the canvas. Carbon dioxide and frozen methane supply tints and shadows. In places that methane's long conversation with ultraviolet light from the distant sun writes the Tholin reds, just as on Pluto, soft pumpkin stains and wine-brown tones on a background of frost. If you have learned to read Pluto's plains and pits, Triton will look familiar, and vice versa. New Horizons data helped here, nudging us to admit the kinship. Two worlds, born likely from the same cold nursery, separated by a gravitational adoption, now show us variations on one theme: how far chemistry can go when sunlight is faint and time is deep. Questions gather at the edge of that theme and ask politely to be let in. If the surface is young, how often is it renewed, and by what combination of frost migration, sublimation, and perhaps cryovolcanism from within? If the atmosphere is a feather, how does it change with Triton's long seasons as the tilted orbit and the planet's path around the sun shift the lighting? If Tholins paint the plains, do they collect in basins and get buried, or do they recycle in slow, wind-driven circuits? We do not have fresh answers because we have not returned. Voyager 2's visit was a single exhale. The decades since have been hours of night where we imagine and model and wait. Still, the outline we hold is strong enough to sit with in a quiet room. Triton is a captured giant among Neptune's moons, a likely exile from the Kuiper Belt whose backward, steep orbit sets it apart from every other big satellite. It dominates its neighborhood, carrying nearly all the mass that circles Neptune other than the planet itself. It is large enough to be round, steady enough to appear nearly the same size in Neptune's sky as the moon does in ours, and gentle enough in relief that a traveler would find horizons unbroken by great mountain walls. Its surface is young in broad swaths, craters scarce, signs of activity present in the form of wind-streaked geyser plumes and wide frost plains. Its colors are the colors of distant chemistry, the blue-white of nitrogen ice, the faint blush of tholins, the clean gray of water ice beneath. And it is kin to Pluto, not only in size, class, and temperature, but in the feel of the place. Broad, level expanses, low relief, a laboratory of slow processes that write their changes in millimeters per year, not meters per day. If Triton once ruled the Kuiper Belt in its neighborhood and was brought in to Neptune, its story becomes a hinge between two regions of the solar system. It tells us that capture is not rare in principle, that binaries can be unraveled by encounters, that irregular moons can be big and round, and still be irregular in the way that matters: direction, inclination, origin. Sometimes the gentlest truths are the ones that stay. Triton's orbit is retrograde and steep about 130 degrees yet round. It holds 99.5% of the mass of Neptune's satellite system. It is the 7th largest moon. It is larger than Pluto. Its surface is mostly nitrogen ice with water and carbon dioxide, with methane altered to tholins painting the red. Craters are few. Youth is implied. The air is thin. Winds draw soft lines. Geysers etch darker streaks across bright fields. The likely path here was capture, perhaps by the breakup of a binary, with tides and time circularizing the orbit and writing the present calm across a once wild arrival. If you let your shoulders soften and your breath find a slower pace, you can hold Triton easily. A pale coin moving backward around a blue giant. A Kuiper Belt traveler turned moon. A world that keeps its voice low but never silent. What Voyager 2 showed us is enough to begin loving the place. A tenderness for a world that makes a new map out of old ice, that keeps the sun's faint light and turns it into weather, that teaches us how origins can be shared even when endings differ. The rest, the interior, the seasons, the detailed chemistry, the full rhythm of its winds awaits a second visitor and a longer listen. Until then, we keep the few frames, the thin air, the backward path, and the kinship to Pluto close, like smooth stones in a pocket, and walk a while longer in the dark with the picture steady in our minds. Life would struggle on Triton's skin. The light is thin, the cold is deep, and the day never warms enough for anything soft to linger at the surface. But surfaces are only first pages. What matters, here, as on other distant worlds, is whether the story keeps going under the cover. Beneath Triton's crust, the sketch many of us carry is of rock and metal at the heart. A dense interior for a moon, close to 2 grams per cubic centimeter, wrapped in layers where ices can flow and, at times, behave like liquids under pressure. That weight explains why Triton outweighs every smaller moon in the solar system put together. There's a large step up from the next biggest Uranian moon, Titania, and the gap shows. With rock at the core comes a quiet heat budget. Radioactive elements decay over eons, seeping warmth into whatever water survives below, perhaps stirring slow convection and setting up a deep kitchen where liquid and stone can trade flavors. That picture rhymes with ones we've learned to love. Europa's hidden sea, Enceladus's breathing cracks, the sense that cold isn't the same as lifeless if there is energy and liquid somewhere close. On Triton, cryovolcanism is written on the plains in modest letters. It isn't the fire fountain kind. It's the upwelling of volatiles water mixed with other ices, maybe a brine softened by ammonia moving through fractures and spreading as flows that freeze into new sheets. In places, Voyager 2's snapshots found plains so smooth and sparse they had the hush of brand new pages, flat expanses bordered by rims, as if a lake had once sat and cooled planitia, solidified cryolava ponds. Elsewhere, the cameras revealed central depressions that look like calderas, places where a chamber roof fell in once the pressure below bled away. If such eruptions rise from a mantle that has water in it, they would bring up more than chill. They'd carry dissolved minerals from the ocean floor, salts and silica, and a cargo of carbon-bearing molecules that might, over time, darken and redden into the tholins we see tar-like organics spun by sunlight and particle radiation from simpler methane and nitrogen. Panels of the surface show long lines running for hundreds of kilometers, simple and elegant as pencil strokes. Faults, most likely, born of global forces. Ice that contracts and fractures as seasons change. Crust that flexes as Triton's path slowly evolves and its interior shrugs. Tectonic hints where plates of ice have been shoved and stretched. In some frames, the ground looks folded and gently buckled, like a blanket pushed by a sleeping body beneath. In others, it is pared down, smoothed by frost and wind, only to be crossed by a recent ribbon of darker fall. This mix of young and younger is the signature, a world that refuses to keep scars for long. The dark ribbons themselves tell a more immediate story. Voyager 2 saw slim, wind-blown plumes, curtains that rose to heights of several kilometers, on the order of 8, and then streamed downwind for 100 or more, laying out dusky fans on the pale plains. These smaller eruptions probably don't tap the deep mantle at all. Triton's sunlight is meager, but it's not nothing. In the right arrangement, it can do focused work. Imagine a clear or translucent slab of nitrogen ice laid across a patch of darker, more light-absorbent material, tholins, dust, some accumulation from earlier breezes. The sun's rays pass through the bright sheet and warm the darkness beneath. Gas builds in the thin gap as the lower layer sublimates. Pressure gathers in silence. Then a seam gives, and the trapped nitrogen rushes out, carrying fine dark grains with it, painting the surface as it falls. It's called a solid-state greenhouse, and it's been invoked on Mars too, where carbon dioxide ice and underlying dust dance to similar choreography at the poles. On Triton, the plume's height and the arrows of its fallout match the theory elegantly. Every fan points the same way in a given region, obedient to a prevailing wind. That wind means there's air, however slight. Triton's atmosphere is fragile, measured then in tens of microbars, akin to what our air feels like at the edge of space, and yet it moves and organizes. Voyager 2 caught clouds riding the lower reaches, streaks and patches casting delicate shadows on the plains. Since that brief hello, models and distant measurements suggest the air can thicken and thin with the shifting seasons, as frost migrates from one hemisphere to another, and a little more nitrogen evaporates under a slightly kinder sun. Like Pluto, Triton wears a haze, hydrocarbon suspended in the thinness, not yet settled into the heavier tholin varnish that stains the ground. A world where ices evaporate and refreeze, where organics settle and lift, where breezes can herd dust into lines and blankets, is a world with weather. Not weather like ours, but weather enough to keep the eye patient. None of that makes the surface friendly. This is not a place to picnic. But world-making doesn't ask for comfort. It asks for process. A rocky, possibly iron-laced core supplies a steady trickle of heat. The mass and composition set Triton apart from mere shards and rubble. Its density tells you it is not just a snowball, and its size tells you gravity has smoothed it into near roundness. That roundness and heft open the door for differentiation. Heavy materials to sink, lighter ones to rise, layers to form, spaces where water can be liquid under pressure. Mix in the energy of tides, Triton's retrograde orbit is still evolving inward, and in earlier epochs, that evolution could have kneaded the interior more vigorously, and you have reasons to expect internal movement. Where there is movement, there can be circulation. Where circulation meets rock, there can be chemistry. Where chemistry and energy linger in a wet place, there can be the slow assembly of complexity. Not a promise, only a path. The younger plains, we saw the soft, fresh sheets, the planitia ringed with low rims, the collapse pits and flow-like textures fit a picture of ongoing renewal. Think of a barely viscous slush warmed from below, creeping out of a vent, ponding and freezing into a level floor. Think of a reservoir below that empties enough to let the roof fail and drop a caldera without the glow we associate with magma, yet born of the same architecture: pressure, release, retreat. These events don't need to be frequent to erase craters and write youth across a landscape. They only need to happen in the last few tens of millions of years, again and again, in small patches, to keep the global count low. In between those long, slow episodes, the solid-state greenhouse plumes write their own diary entries. The direction of the fans marks the wind of that season. Their length speaks to how long a vent lasted before pressure eased or light shifted. Their overlap tells which was older by a day or a week. Even clouds give an index of the air's brief moods. Thin streaks that form and fade over bright fields. Misty veils that hover just a little above the ground and then vanish in the general cold. It's all so delicate that you must remind yourself what you're seeing. The behavior of nitrogen, a gas we are used to ignoring, here freezing, sublimating, and moving the way water does at home. The same element wears different costumes depending on how far from the sun it stands. If the deeper cryovolcanism taps something wetter and warmer, the surface may hold a loose sampling of the ocean's pantry. Salts, carbonates, silica, organics, riding up in a spray and settling as dust. Tholins themselves are more likely a product of sunlight high in the air and chemistry on the ground, but they need feedstock, simple molecules to polymerize and brown. That feedstock can come from the sky or from the sea. On Triton, it probably comes from both. If beneath the ice, water meets rock in the presence of heat, you could imagine environments not unlike the deep-sea vents on Earth. Gradients to mine, minerals to build with, patience enough for molecules to try configurations until some of them stick. Nothing guarantees life in such places, but such places are among the few where life feels imaginable without the sun at all. Breathe a little more deeply and let the larger arc settle. We've walked, tonight, through a family of eruptions. From Earth's ocean lifting fire into afternoon, to moons that exhale in their sleep. Io, with tides that knead rock into magma and fountains that paint sulfur crowns on the dark. Enceladus, with its tiger stripes and bright breath, a white pearl writing a blue ring from an ocean we can't yet touch. Triton, a captured traveler moving backward around a distant giant, resurfacing itself with cold eruptions and whisper-thin weather. The forms differ: lava lakes and overturned crusts, water plumes that join a ring, nitrogen curtains that sweep downwind, but the heart is shared. Stress turned into heat, heat turned into motion, motion turned into change you can see from far away. What we call the biggest ever eruption in space looks different when you let it rest among these companions. The Hunga Tonga Hunga Ha'apai blast carved a pressure ring into the sky that lapped the world. It was immense in a human sense, fast and loud and right here. Io's umbrellas of ash and so too reach higher than any thunderhead, changing a moon's air in a few minutes. Enceladus lists its exhalations into a planet-wide scarf you can only see when the sun is just so. Triton draws thin black lines you could follow for 100 kilometers with a fingertip. Scale is not only about size, it's about the way energy leaves a body and enters a story. Some eruptions we feel in our windows, some we feel in data and in the hush between frames. If your heart wants something small to hold on to before sleep, take a few stones. Triton's density, telling of rock and metal. A surface young, because cold eruptions keep repainting it. Planitia, like frozen lakes rimmed by low walls. Calderas, where roofs fell when the pressure ebbed. Wind-blown plumes, rising to several kilometers and laying down fans that all point the same way. An atmosphere so thin it would feel like the very top of our sky, yet lively enough for clouds. Haze, born from hydrocarbons, not yet aged into tholins. Long faults like handwriting. A backward, nearly circular orbit that speaks of capture and of tides that smooth and tug over ages. None of these by itself is extraordinary. Together, they make a place you can love from far away. We do not have the next visitor lined up with a ticket in hand. The spacecraft that skimmed Neptune's realm has long since left the stage. The instruments that tasted Enceladus's breath are ash in Saturn's air. Plans for new eyes on the outer dark sit in drawers and on whiteboards, waiting for time and means. That can feel like an ache. But the maps and spectra we have are richer than they first appear, and the patience of small worlds is greater than ours. They will still be there when we are ready. Perhaps one day a probe will slip through Triton's haze and circle for a season, watching the fans grow and fade, feeling the air's slight hand, listening for heat under the ice. Perhaps another will fly through Enceladus's plume with a better nose, or watch Io's lava lakes overturn in slow waves, or catch, from some safe distance, the breath of another earthly sea, lifting a voice into the sky. If your heart says yes, a quiet like and a soft subscribe would be lovely. Then let the numbers dim in your mind until they are just warmth in the pocket, tidal rhythms, densities, distances, tiny atmospheres, slow eruptions, and let the images float. A blue ring against black, a yellow moon with a dark lake, a pale world with a thin plume writing a line for the wind to read, a wide ocean on our own planet remembering that its floor is a volcano's roof. Rest your shoulders. Close your eyes. The universe is still telling itself the story of how heat becomes motion, and motion becomes shape, and we're lucky enough to have heard a few chapters. When you wake, the giants will still be turning, the small worlds will still be breathing, and the sky will still be wide enough to hold another question.